Welcome to Scale Up University. Welcome to the course on designing data intensive applications. So, this is the lecture 5 of module 1. And in this lecture, we will be discussing the difference between faults and failures, like faults versus failures. So, these two terms are like very different. So, if we talk about the lecture overview, like what exactly we will be discussing in this lecture. So, like in distributed systems, something is always failing. You just don't know what yet. And that's like a harsh reality of a distributed systems wherein something is always failing and we are just unaware of that. Now, beginners, they assume that systems are perfect, they run correctly. Beginners, they assume that unless something unusual happens, system will keep on running perfectly. But the harsh reality is that hardware is constantly degrading. Networks are constantly dropping packets. Software has undiscovered bugs, and humans make mistakes daily. And because of all these reality, systems cannot run correctly. Because in a system, something is always failing. It might be the hardware, it might be the network, it might be some undiscovered bugs in the software, or some human mistakes. And that is what we will discuss in this lecture. So, this lecture explains. So, in this lecture, we will get an idea about what a fault is, what a failure is. So, you will get a very clear understanding between the difference between the fault and the failure. This lecture will also give you an understanding why faults are normal in computing systems and why systems must be designed around that truth. So, whenever we are doing a system design, we have to keep in mind, we have to consider faults to be normal. We have to consider faults as a part of harsh reality. We have to take into consideration. We cannot assume a perfect system and design system accordingly. Rather, we should assume an imperfect system with faults in place, and we have to design systems accordingly. And the main goal is to make the system reliable by handling the faults gracefully. That's the main idea. So, that is what we will discuss in this lecture. So, if we look at the topics that we will cover in this lecture, so we'll talk about precise definitions, why faults are normal, not exceptional, types of faults, designing for failure, not avoiding it. And we will conclude this lecture by discussing fault tolerance versus fault avoidance. So, all these topics we will cover in this lecture itself one by one. So, this is the module 1 trade offs in data systems architecture, lecture 5 faults versus failures. And we are starting with the first topic, that is the precise definitions. So, if we talk about fault, like what is a fault? So, fault is basically a defect or abnormal condition in one component of a system. So, any defect or abnormal condition in one component of a system is said to be a fault. Now, if I talk about fault, it may exist silently, it may not immediately cause system wide impact. So that is something very dangerous about the fault. Now, fault is very clear to us that any defect or abnormal condition in a component of a system rather than the system as a whole. And one very harsh reality about the fault is it may exist silently, wherein its impact, its immediate cause, like it the fault might not have system wide impact, and hence we are unaware of its existence. If we talk about the examples of the fault, so defect or abnormal condition in one component, so we can have something like disk sector unreadable. Now, this is a fault because it has to do with just one component, that is the disk. Network cable unplugged, because disk network, they are the part of the system. So here the issue is not with the entire system rather than a component of the system, and hence these are examples of fault. Disk sector unreadable, network cable unplugged, bug in line of code, configuration misset. So these all are examples between the examples of the faults. Now, if I talk about failure, what do we mean by failure? So when the system as a whole stops providing correct service. So failure is something which has to do with the system as a whole. So when the system as a whole stops providing correct service, we say that there is a system failure. And fault is like a defect or abnormal condition in one component of a system. So difference is now very clear. Failure means system level, when the system as a whole stops providing correct service. If we talk about examples of system failure, so let us suppose user is not able to log in, data corrupted. Because when users cannot log in, it's a system failure because multiple issues might be there. There can be multiple reasons because of which the user is not able to log in. There might be some issue in the code, in the database, in some network. Data corrupted. If data gets corrupted, system will get corrupted. So it's like a failure. It's an example of a failure. Transactions duplicated. If transactions get duplicated, it will lead to system failure because many components at the same time will get affected. And if system crashes as a whole, then it's a system, it's a failure because now it's very clear that all these examples, like they are stopping, like they are like not letting system to provide correct services, and hence they are examples of failure. If we talk about the relationship between fault and failure, so fault, we are already aware that fault is something with one component of a system, like abnormal condition or defect in one component of a system. That's a fault. Now, if the fault is unhandled, then it will lead to failure. So unhandled fault will lead to failure. So very important learning, not every fault causes failure. So this is very important because see, not all faults are dangerous. There are many faults which the system might tolerate, but there are certain faults which might be dangerous wherein it can lead to the failure of the system. So not every fault causes failure. So this is something very, very important you should be aware of. So now in system design, the difference between fault and failure is very important. Now I hope you got a very good understanding about the, like, what exactly is the meaning of fault, what exactly is the meaning of failure, and the difference between the fault and the failure, and and also one very important observation that not every fault causes failure. If we talk about reliable systems that we discussed in some good detail in the previous lecture, like reliable systems, if we talk about, now they can detect faults. Reliable systems can detect faults, they can contain faults, they can prevent faults from escalating into failures. Because reliable systems means systems can handle faults and failures gracefully. And how they can handle faults is, first they have to detect faults, they have to contain faults, and they have to prevent faults from escalating into failures. In this way, they can gracefully handle the faults. Now we can discuss one very important insight. So see, faults are component level problems and failures are system level breakdowns. This we already saw. And reliability is about preventing faults from becoming failures. So that is the reliability. Why faults are normal, not exceptional? So if we talk about the reality of large systems, so see, the idea is that if you are dealing with just one machine, in that scenario, the failures might be very rare because if you are using like a very small system, like just one machine, but if you are using 10 machines, then you will get weekly failures, like failures every week. And if you're using 10,000 machines, so here you can consider it as nodes as well, then failures you will see constantly. So the idea is that as we are adding more and more nodes, we are making system more and more complex, failures will become normal. So the idea is, at scale, failures are statistically guaranteed. So this is like a very important observation. And see, any software, like at after a point of time, it has to scale. Like any web application, it scales. And when we keep on scaling it, failures are statistically guaranteed. So if you are involved in like a system design of a like a very big web application with huge traffic, and if you are trying to scale it, then you will frequently come across failures. So failures are statistically guaranteed. So if we look at the statistical perspective, so even if each disk has 99.99% reliability with thousands of disks, some disks are always failing. So let us suppose you are using a disk with 99.99% reliability, and if you are using those disks, and if you are using thousands of those disks, some disk you will find they're always failing. So the moral is, probability compounds at scale. Probabilities, they compound at scale. Okay, now we'll discuss the next very important observation, that is the distributed systems insight. So if we talk about distributed systems, in distributed systems, partial failures is the norm. And in if I talk about partial failure, I'm talking that some nodes are down, then it's a partial failure. So see, in distributed system, partial failure is something which is like very normal. You will always see some nodes are down, or some nodes are slow, or you see that some messages are lost. So these are examples of some like failures in distributed systems, like some nodes are always down, some nodes are slow, some messages are lost. So in a distributed system, you're always operating in a degraded state. Okay, now we'll discuss cultural shift required. So see, now it is like a very important discussion, like in system design. So in system design, the traditional thinking was we must prevent faults. So traditionally, our mindset was, let us design a system in such a way that let us focus on preventing faults. But it is very tough, because faults is something which is not in our control. So there is a need for the shift in the mindset. So there is a need that you should prevent faults. Like you should not think about preventing fault. Rather, you should assume fault as normal. They will occur, and you should plan to handle those faults. So modern distributed thinking, according to this, faults will happen. We have to assume that faults will happen, and we have to answer this question: how do we survive them? So designing modern distributed systems is all about designing ways, or identifying ways, to handle faults and failures gracefully. So system design is all about reliability, wherein we assume system will be having faults and failures, and we have to find mechanisms to handle faults and failures gracefully. So that is the idea. Types of faults. So if we talk about types of faults, so faults, we know that it is like a abnormal condition or defect in a single component of a system. That is a fault. So we can have something called as hardware faults. So as the name suggests, some issue is there in the hardware component. That's the hardware fault. For example, disk crash, power outage, memory bit flag 01, network switch failure, CPU overheating. So these are some faults in a individual component like disk, power, memory, network, CPU. Now, very big question in front of us: why hardware fault occurs? Like why hardware fails? Like why disk crash? Why memory bit might flip So if memory bit flips, data gets corrupted. Why network switch failure might occur? Why CPU might overheat? So if I have to answer why hardware fails, then I have to think like this. So see, physical wear, because hardware is like a physical device, it can wear out. Some manufacturing defect it might contain, and that might get propagate. Environmental factors, like let us suppose if the outside temperature is very high, then CPU overheating might occur. Cosmic radiation. So like under very high frequencies, memory bit it might get flipped. It might get flipped, and hence data might get corrupted. And power instability. And because of power instability, also hardware might fail. So hardware fault is very clear to us when there is any defect or abnormal condition in the hardware, and why it occurs, that is also very clear. Now, if we talk about some modern reality, so see, hardware reliability has improved, but still with the scale, failure probability increases. So scale increases failure probability. And if I talk about cloud providers, they also expect hardware to fail, and they keep on replacing machines routinely. So now it's very clear that because if I talk about modern reality is scalable applications. So we already saw that with scale, failure probability it increases. Modern reality is cloud computing, wherein all the web applications they are cloud native in nature. They are deployed on cloud. So cloud also they expect hardwares to fail, and they keep on replacing machines routinely. So modern reality is hardware faults are expected. Like hardware fault is something which you should always assume in your system design. You should consider hardware fault to be a normal. So the key strategy is, so instead of buying perfect hardware, one should focus on replication, wherein adding multiple backup nodes, use redundancy, and use automatic failover. So this is very important. So now it's very clear that if I talk about hardware faults, we have to assume it. And in system design, instead of focusing on buying perfect hardware, we should focus on arranging backup nodes, using redundancy, and using automatic failover. Software bugs. So if I talk about examples of software bugs, so the software bugs means bug in the software. It's very common, like some race conditions, memory leaks, deadlocks, incorrect assumptions, edge cases not handled. All these can lead to, like all these are examples of software bugs. Now, why software bugs are dangerous? So unlike hardware faults, software bugs can affect all nodes simultaneously. Okay, so this is very interesting and very important discussion we are making. So see, why software bugs are more dangerous than hardware faults? Because in hardware fault, any fault in a hardware, it will stay till there, because that fault will not migrate, it will not get propagated. Because if a fault is there in the disk, it will remain in the disk itself, it will not get propagated. But if I talk about software, software is something like which covers the entire system, because a system can made up of a lot number of components. Now software it gets spread across all the components. So software bugs can affect all the nodes simultaneously. Bugs are systematic, not random, and bugs can be reproduced under certain conditions. So that's why software bugs can lead to system failure. So systemic risk is there, and hence software bugs are very dangerous and critical in nature. One example we can see, a bad update deployed to all servers. Let us suppose to all servers, if a bad update is deployed, all instances crash at once. Software faults are correlated failures. Okay, so software faults are very dangerous and they can very easily lead to failure, because softwares are spread across all the components. So a small bug can lead to the collapse of the entire system, leading to system failure. Now, one very important point. So you will say that, okay, software bugs are dangerous. So let us rigorously test softwares. So now we'll discuss why testing is not enough. So testing is important, but it's not enough. And why is it so? Because see, in testing, we are trying to simulate use cases. Now it's impossible to simulate all states. There might be many use cases which we might miss out. So it's impossible to simulate all states. Distributed systems have enormous state spaces. And see, distributed systems have enormous state spaces. They have many use cases, and it's nearly impossible to simulate all of them. Race conditions appear under load. Rate timing conditions are hard to reproduce. Software reliability is probabilistic, it's not guaranteed. So see, the idea is that, let us suppose you do rigorous testing. You put lots of effort in testing the system. Still, there might be many use cases, many scenarios which will be left for testing. Like you will not be able to test them. And also software reliability is probabilistic, not guaranteed, because we cannot test all the states simultaneously, and hence testing is not enough. So the idea is that, let us suppose you designed a system, you tested it rigorously, and with the test results you are happy that, oh, finally I made something very stable. But after a point of time, that system might encounter some unexplored use cases, and the system might collapse also. So that's the idea. Okay, then we have human or operational error. Because see, humans who will be operating the system, they can also make mistakes, and that is what we are discussing now. If we look at the examples, like what mistakes human operators might perform, or human operational errors, if we talk about deleting the wrong database, misconfiguring firewall rules, because these are human errors. By mistake, the developer might delete a wrong database, firewall rules might be misconfigured, deploying broken code, rotating keys incorrectly. So all these are examples of human errors. Now, if we talk about the hard truth concerning the human error, okay, so the idea is that in any system, the hardware fault is like very less in number. Like if you are looking at this pie, just a small piece of it is the hardware fault, and rest all is the human error. So most major outages are caused by humans, not hardware. So this is a very, very important observation. So in any system, like a distributed system you can take with many nodes, there you will see that hardware faults will be very less in number, and human errors will be a lot more. Now, why is it so? Now let us understand why is it so. Because if we talk about humans, they can misinterpret documentation, they can forget dependencies, they can act under pressure. And hence, we can say that human errors are inevitable, because humans can make mistakes, because if they are acting under pressure, they might forget dependencies, they might misinterpret documentation, and they might end up in like producing errors. So see, systems are complex, interfaces are confusing, time pressure exists, and knowledge is incomplete. So see, basically why human errors are inevitable, because humans, they are dealing with complex systems, confusing interfaces, they are operating under high pressure, time pressure is there, and they might have incomplete knowledge. And because of all these factors, like if a human is involved in a complex system, he might end up making many human errors. If a human is interacting with a confusing interface, he might end up in making many human errors. If time pressure is there, humans might make human errors. And if the human is not properly skilled, he is having incomplete knowledge, then also human errors might occur. So the moral of the story is you cannot eliminate human mistakes. So this is very, very important. So when we are doing the system design, we also have to consider the scenarios wherein humans can make mistakes, and we have to plan how to handle that. So we must design around them. So we cannot eliminate human mistakes. So any system design we are doing, human mistakes we have to take into consideration, and we must design our system around them, assuming that humans will make mistakes, and we have to handle those mistakes gracefully. And that is what system design is all about. Designing for failure, not avoiding it. So see, if we talk about previous like traditional design thinking, we already saw it was aiming for it was aiming to prevent faults at all costs. So traditional design thinking was all about preventing faults, assuming rare failure, and optimizing for normal cases. So it focused on perfect operation. But if we talk about modern thinking, modern distributed design, it's a modern approach. Now, this modern approach, it by default assumes faults. And since it by default assumes faults, it has mechanisms to detect faults quickly, isolate damage, and recover automatically. So there is a design principle in place for failure. So to handle system level failure, what all we can do to handle system level failure gracefully, we should be having redundancy. Redundancy means multiple copies of the same node, so that if any node gets corrupted or if any node is down, we can make use of the backup nodes. So redundancy means multiple copies of the same node. Isolation is a sort of a modularity also, you can say that, wherein components, they work in isolation, like they might exchange information, but component A and component B should work independently. That's the isolation. The good thing is that with isolation, if let us suppose component A got it gets damaged, then still it will not have much effect, much influence on component B, because component B, whatever code functionality it has got, it will work, it will accomplish that. And only whatever dependencies component B had on component A, there it might fail, because component A is not working, it's crashed. So component B might face some challenges, but all the independent functionalities of component B, it will keep on running. Monitoring and alerting. So if I talk about design principles for failure, so if you want to make a reliable system wherein we should be able to handle the failures gracefully, monitoring and alerting is very important, wherein the system should keep on monitoring whether something is wrong, and if it is so, alert mechanism should be there. Graceful degradation and automatic automatic recovery. Okay, so graceful degradation means rather than the complete shutdown of the system, it should be gradual. Like we should reduce some functionality, then some more, like that we should keep on doing it. So that is the graceful degradation. And automatic recovery. So automatic recovery means we should recover. So we should re-replicate data, restart services, and rebalance traffic. So automatic recovery means if something goes wrong, since backup nodes are always there in place, we should be able to make use of that. Okay, now we'll discuss the failure first mindset. So the failure first mindset is during the system design itself, we have to consider failure like a very common think, and we should ask questions like, what if this node crashes? What if the network is partitioned? What if this message is duplicated? What if two writes happen simultaneously? So all these answers we have to have before system design, so that when we are designing systems, we are handling all these scenarios. And if we are handling all these scenarios, we are handling the failure. So if you do not answer these questions early, you have to answer them in production. Because if you answer them early, then the system you will launch, it will be like very reliable. But if you don't answer this question early, then your system might face lots of problem, and then you will be needing to answer these questions. Fault tolerance versus fault avoidance. So these two terms look very similar, because if I ask you the difference, you might get confused, because both are very similar: fault avoidance and fault tolerance. Now see, fault avoidance means we are avoiding the fault. Avoiding the fault means we are not at all letting the fault happen. So it's like a shield. Fault avoidance means it's like a shield. It is not letting the fault to happen. So it's a proactive approach. So fault avoidance is a proactive approach wherein we not at all let the fault to happen. So it is prevention. Avoidance means prevention. So we are preventing the problem. So we design, test, and verify. So how we can achieve fault avoidance is, first we should design the system, test it, and verify it. So that if we feel like some fault might occur, so beforehand we are preventing it to occur. So that's a proactive approach. And fault tolerance means it's a reactive or adaptive approach wherein fault already has occurred. In fault avoidance, fault has not occurred. It's about shielding the fault, preventing the problem. But in fault tolerance, fault has already occurred. Now, how to handle it? It's a reactive approach, adaptive approach. So fault tolerance means continue working. The show must go on. The system should keep on working despite the fault. So that's the fault tolerance. We're tolerating the fault. So continue working despite problems. And we are able to tolerate fault because of redundancy. So if we have redundancy in place, recoverability and resilience, all these will lead towards fault tolerance, wherein if fault also occurs, we will be able to handle it because of redundancy, recoverability, and resilience. So see, fault prevention, fault avoidance is something which is like a very hypothetical situation, because already we saw in system design, like when we scale the system, faults are something which are very normal, which are very common. And if faults are very common, normal, we cannot avoid it. We have to rather handle it. So very important observation. At scale, if we talk about, fault tolerance is the only viable strategy. So at scale, fault tolerance is the only viable strategy. So finally, we completed this lecture. So in this lecture, we got a very important understanding that fault is not equal to failure. Fault is something which is like a component level, a defect or a abnormal condition in the component of a system. But failure means system level failure. Means if there is a failure, then system will not function at all. And we also saw that faults are inevitable at scale. At scale, faults are very normal. They are inevitable. We cannot avoid it. Rather, we have to handle it. We have to tolerate it. So fault tolerance. We also saw hardware faults are random in nature, and software bugs are more systematic and more dangerous, because software bugs, they can penetrate the entire system, and they can like collapse the entire system. But hardware faults, they don't propagate, like it does not have that impact. Only that particular component might get disturbed. So in some scenarios, hardware fault might lead to system crash. It might happen. But there might be scenarios also wherein we can tolerate hardware faults. And we also saw human errors are something which is unavoidable. humans can make mistakes, because while testing also we cannot consider all the possible scenarios. There might be some scenarios which we might miss out. So human errors are unavoidable, and we have to take that also into consideration while system design. And reliability requires designing for failure. So a very important key takeaway from this lecture is that as system design engineers, or as engineers responsible for designing data intensive systems for data intensive applications, the question is not will something fail, rather we will assume all the things to fail, we'll assume it. And the question now it will get changed to how will your system behave when it fails, to ensure reliability. So finally we completed this lecture. I hope you got a very good understanding of the concepts which we covered. So do subscribe to our YouTube channel Scale Up University for more such interesting lectures and courses. Thanks for watching. Thanks for your time.